Hi, this is Aaron Jerome with Jerome Electronics, a YouTube channel. Today we're going to be presenting the second video in the Vivado HDL group. Last time was part one, where we went through how to find and install Vivado. This time is part two. We're building a comparator. And I generally start by telling my students something about a kind of a big word that some of them haven't heard of before. The word is abstraction. So to understand abstractions, there are higher levels of abstraction and lower levels of abstraction. And when we start with abstractions, we start with transistors. Transistors are the tool that we use, and I've got a whole video on transistors if you want to know more about that, but they are the tool that we use to build logic gates. And when you combine those logic gates into bigger and bigger components, you can build other mini components that computers use all the time. So, for example, in our class, the components that we've been building with logic gates just lately are event detectors, shift registers, binary counters. We did a calculator back a little while ago. All these are just small but greater abstractions. They're greater than just the logic gates. We built the logic gates to do these small kind of units of artificial intelligence. So that's what we're going to do here, and when we're going to build something called a comparator, and if you understand the image I've got there, then you understand what a comparator does. So we'll get into that, but the abstraction idea, you keep building into greater and greater abstraction. Perhaps the next level of abstraction might be an arithmetic logic unit, or a even greater central processing unit. Different kinds of components that computers use to serve mankind. We're getting into greater and greater abstractions when we get into things like artificial intelligence, whether it's machine-driven artificial intelligence or human-driven artificial intelligence, and that's kind of what we do, is the human-driven artificial intelligence. So let's get into this. Here is the worksheet that I will print and hand out to my students so that they can follow along with what we're talking about. So let's get into it. This is a comparator. This is meant to represent a physical comparator where we can put box X, which is meant to represent a variable, and box Y, which is also meant to represent a variable, on a balance, and if they weigh the same, then the balance will tell us that X equals Y. But that has to do with weight. What a comparator does is the same thing, but it does it with the value of the number. So, in this case, if X happens to be the greater value number, then the balance will point to X is greater than Y, right? And then if they're equal in value, then the balance will point at X is equal to Y. And if X is less than Y, then the balance will point to X is less than Y. And we can also, these variables are, we don't know what the actual value is, but if we take the boxes off, then we can see what the actual value is, and we would expect the balance to point at X is greater than 1 if 1 is on one tray and the 0 is on the other tray. And if we trade them, so what we've really done now is made X equal to 0 and Y equal to 1. So what that will do is that will say, okay, now X is less than 1. And of course, if we switch it so that they're both 1s, then that should balance out. And that's what a comparator does. Now, if we were to build an actual comparator, well, let's just say we simulated one, say, on multisim, it might look something like this. These are the gates that we might put together, and the outputs tell us that A is A is less than B, or A is equal to B, or A is greater than B. But we want to skip the simulator part here. That's the benefit of Vivado. So what we're really interested in is the actual equations that we pull from this idea. So in reality, then, all we need is the Boolean equation. So this is a byte of digits. A byte is 8 digits, and we're going to call this byte X. And this is going to be another byte, and it's going to be byte Y. And what we're trying to learn how to do is instantly see which of these two bytes is the greatest. And if we can understand how we figure that out, then we can teach a computer how to do it. So we look at these two numbers and we look at which one is greater. And what I'd prefer that you do, and in my class we stop here, so you could stop the video, but then, figure it out, which of these numbers is greater, and how did you know, and how did you figure that out, and how are we going to teach a computer how to do that? Okay, just a pause so you could stop the video there. Here we go again. So here's how we do it. What we have to do is we have to put the column weights above the numbers. And that's what I'm doing now. 1, 2, 4, 8, 16, 32, 64, and 128. Above each of the numbers in the columns. And now we can start at the most significant bit. That's over there on the left. The least significant bit is over there on the right. Starting with the most significant bit, all we really need to do is compare those two numbers. If one of them's greater, the whole byte is greater. Well, in this case, neither of them is greater. Okay, so a computer will learn this by comparing one column at a time, starting at the MSB, and it will look at those and it will compare the bits, and then it needs to report back to us if they're greater, if X is greater than Y, if X is less than Y, or if X is equal to Y. So if the top bit was greater, that would mean X is 1 and Y is 0. Well, that would mean the whole byte X is greater because the column weights are twice as heavy as the next column. So that would be the greatest number. If the bottom were greater, then X would be 0, Y would be 1. All we care about then in that byte is which of these two is greater. But if they are the same, what do? Well, if they're same, we have to move to the next column and repeat the comparison. So next column in the MSB, we're comparing these two. We're in the 64 weighted column. They're the same too. So we've got to move to the next column because there's no way to tell which byte is greater from the first three columns. And so we're going to compare this column. Now in this column, we actually have a result. We know that the top number in this column is a 1 and the bottom is a 0, and we found it. It's if that 1 is greater than the 0 in the bottom column, then we've actually found which of the bytes is greater. This is the greatest number. Okay, so now our task, now that we understand how to determine which of these bytes is greater, we want to teach the computer how to do this. So what we're going to do in this case, if you remember back, there are steps to getting an idea from your head and building it into a marketable product. And that's really all I've been teaching over and over and over again, different ways throughout all this class. You take an idea from your head and you turn that into artificial intelligence doing the same thing, and then have a machine do it after that. So the steps are, you have an idea, you get it down on paper somehow, you take whatever that is, whether it's a written statement or a bubble graph as the representation of the idea, or in this case what we're going to do is draw a picture of the representation of the original idea. Whatever it is, we got to get it on paper, and then we will put it into a truth table. So what we're going to do is build a machine that can compare 2 bits at a time. 2 bits, not 2 bytes. So we really can just start out here by saying, well, let's just take a box. Here's a box, and we're going to give it a simple name. comp, which is an abbreviation of comparator, and then we're going to give it a simple thought. The simple thought is a question: is x greater than y? And then we're going to give this box some inputs. Now, you probably are thinking ahead of me. What you should be doing is writing this down. If you can think ahead of me on this idea, you should try to work faster than me. But what I'm saying is we need to put the value of x in here, and we need to put the value of y in here. So we're going to represent it with these arrows called x and y's, but what we're really calling them is ports. Sometimes I call them doors. And these are ports where values can go into this box. So we'll need a way to put the value in the box for x and a value in the box for y. And of course, we're going to need some outputs. And the outputs that we're going to put on this box, we're going to say, okay, if x is greater than y, then we're going to put a 1 in the output GO, which means greater than output, okay? And, well, if it's greater than, but we also need an output so that we can represent less than and equal to, but we can do it with 2 outputs. So we're going to make another output called less than. So we got a greater than output port and a less than output port. If x is greater than y, we'll put a 1 in the GO output. If x is less than y, we'll put a 1 in the less than output. What if they're equal? Well, equal means that neither of them are greater than the other, so we would just put a 0 into both, and a 0 in both means that they are equal to each other. Okay, so now this is all we need to get our truth table. We have this idea, we pulled it from our mind, we put it on a paper, we've mapped it out, and so now we need our truth table. We have a truth table that will need columns X and Y, and we're going to need some outputs GO and LO. Now on your paper, maybe you've sketched this comparator box, but on your paper, there's a truth table. If you will put X and Y in the input columns at the right and leave the left columns blank for now. We'll get into those in a minute, okay? So we've got a truth table. You know that the inputs are X and Y. You know that the outputs are GO and LO. And I also have my index column there where we're numbering the rows so we can always address which one we're talking about and not get confused. And you remember that we always just count in binary for the inputs. That ensures that we consider every possible combination of X and Y. Then what we're going to do is we're going to get that thought that we have for the box. And we're going to ask the question, for row 0, is X greater than Y? If it was, we'd put a 1 in GO, right? And so X is not greater than Y in this instance, and so GO is 0. And then we kind of think, well, is it less than Y? So that would be X. Is X greater than Y? False. And so if that's not true either, we would put a 0 into the LO column for row 0. Then we go to the next column and we ask our question again. Is X greater than Y? And in this case, X is not greater than Y. So we're going to put a 0 in the GO column. And then we're going to say, well, if it's false, well, that means Y is greater than X. If X is less than Y, we will put a Y in the less than output column. Hopefully you're seeing how this is all working. Going to the next row, in this case what we've got is X does happen to be greater than Y, so we will put a 1 in the greater than output port. X is not less than Y, and so we won't put a 1 in the less than output, we will put a 0. In this last row of this truth table, it is indicating that X and Y, X is greater than Y and Y is greater than X, and that's not true, so they're both false, so we're putting a 0, 0 in this. Is X greater than Y? False. Is Y greater than X? False. Is X less than Y? False. So these are both zeros. At this point, there will be times when the comparator doesn't know whether they're greater or less. Maybe both x and y are zeros, or x and y are both ones, and it just could not tell whether or not one was greater than the other, or x was greater than y, or x was less than y. So it has to go to the next column. Since these bits are the same, the next column might be the true indicator of greatness. To go to the next column and make that comparison, we don't actually move the comparator itself. What we can do is just make a copy of the original comparator, and then we're going to call that comp1. And when we do that, then now we have another comparator. We would just, rubber stamp these, duplicate them, copy and paste them for 8 different bits, and so we would do the whole byte using 8 of these little comparator components. Okay, so that tells us that we're actually going to need to change these comparators, because the new comparator is going to need to know whether or not the previous comparator found the result to be greater or less than, or didn't find results at all. So to receive the results of comparator 0, we're going to add some input ports to the new comparator, and we're going to call those greater than in and less than in, and they will receive the value from greater than out and less than out. And if they receive a 1 in either the greater than ports or a 1 from the less than ports, what they're supposed to do is pass that information through, and they don't actually have to compare x and y. However, if the greater than and the less than inputs are zeros, that is an indication that nothing has been found yet. We don't know whether x byte or y byte is the greater byte. What that tells us is that we also need to put those inputs on the first comparator, comparator 1, and that way we've got one component that we can duplicate for as many columns as we want to compare. So we need to put the greater than and the less than inputs on the original comparator as well. Now, since the truth table is addressing the first component, then we actually have to expand the truth table to include these new inputs. Now, instead of 2 inputs, 2 to the power of 2 is 4. That's why we have 4 rows. But now we have 4 inputs. 2 to the 4th power is going to be 16 rows. So we're going to have to expand our truth table and put the new inputs on our truth table, and that with 4 inputs, 2 to the 4th power, we're going to need a total of 16 rows on our truth table. I've got them all indexed 0 through 15. That's 16 rows. I'm going to just count the rows in binary so that we can ensure that we have every possible combination of these 4 inputs. And then I'm going to start populating the outputs for what I think should happen in every instance on every row. So now, from the previous comparator, nothing was found. That means GI and LI doesn't know, and they send 0, 0 if they don't know from the previous comparison. Or if there isn't a previous comparator, we still have these inputs, and we can just hard code them, set them to zeros, and that way we can use this as the first comparator. What that means then is that the value of x and y that we just figured out a few minutes ago are going to be the same. Since GI and LI are 0 in these rows 0 through 3, they don't influence the results. We don't know yet whether or not x is greater than y or x is less than y. So now GO and LO will be the same values as before, since the GI and LI being at 0 means we don't know yet from the previous operation. So now we're comparing x and y again, and is x greater than y? No. Is x less than y? No. So false, false. We're going to put zeros in when it's false. In row 1, is x greater than y? And is x less than y is the next question. No, and so we would actually put a 1 in the output so that x is less than y in this instance. On the next row, x happens to be greater than y, so that is true for the output GO. Is x less than y, and that is a false statement. And then in the last row, is x greater than y? No. Is x less than y? No. So these are the outputs that we found a few minutes ago. But now with the next group of 4 inputs, the ones in the LI column indicate that in a previous operation, in a previous comparator, we have found that x is less than y, and we have 4 possibilities where that has happened, regardless of what x and y are currently. If we have already found that x is less than y, then we simply just pass that information through. So the values in x and y make no difference, since we already know that the previous greater column weight produced a value that was where x was less than y. So the results just pass through. X is still less than y. So we can just put those as the outputs as in the GO and LO columns. In rows 8 through 11, the previous instantiation of this comparator has found that x was in that column greater than y. And so greater than in gets a 1 for all 4 of these rows, and that is simply passed through, and we don't care what x and y are because we've already found that in the previous greater weighted column, x was greater than y. So again, the results are simply passed through. And in these cases, we know that byte x is greater than y in all of these instances. Not because of this comparator, but from previous information probably discovered by a previous comparator. In the last 4 rows, 12, 13, 14, and 15, the previous comparator found that x is greater than y, and it found that x is also less than y. Well, that's impossible. X cannot be both greater than y and also less than y. What that means is that we have some don't cares in the truth table. We needed those combinations to be addressed, but we know that it won't happen, so we're going to replace these outputs with wildcards. And so we've considered every possible combination and what it should mean. So the don't cares, we have to include those too, because if you remember, they are useful for K-map simplification, which is what we're going to do next, because this truth table for the comparator has been finished. So now on your worksheet, I have set up, or at least given you a grid for a comparator, and we're going to simplify the GO column with this K-map. Now, my students know this well. This is a really good time to stop the video at any point where you think you can do this work faster than me. I'm going to be going kind of slow so that I can address all the details. But this is going to be the K-map for GO. Now, I'm going to do something that I haven't been doing a lot. I'm going to set this up with the GI and LI on the top. And there's GI, double knot, left knot, no knot, and right knot above the columns. Right away, because I've made the decision to put the GI first, and because GI is the first on the left in the truth table, the cell numbers will always go away from that first variable in the truth table. That means this time the values or the cell numbers are going to be going vertically. They're going to be progressing vertically instead of horizontally. On the side, we're going to put X and Y with double knot, left knot, no knot, and right knot. And then we're going to populate this K-map with the first 4 values from the GO column of the output. So it's 0, 0, skip, go to the bottom one, go back. So filling it in for the next 4, 0, 0, skip, go back. Next, we're going to skip a whole column. So these ones will go in the last column. And then we have to put the X's in, skipping and going back. Having done this, we are ready to implicate. We want to implicate the biggest groups of ones we possibly can. We cannot implicate a group of 16, but we can implicate a group of 8 this time. So that's what I'm doing. There is a group of 8. Remember, the X's are wildcards. We can call them 1s if it helps. And what that means is we've implicated from the top to the bottom of the K-map. That means all of the values on the side are canceled out. And so all we have to do is worry about the values on the top, the variables on the top, and it looks like Li and Li are opposites of each other, so they will not be in our solution. The only thing that will be in the solution of this implication is going to be Gi. But we have one unimplicated 1 on this K-map still. So we're going to implicate that by crossing the boundaries. And then we have to keep X not Y in our solution, in our simplified equation, because there's nothing to compare and cancel against. But up at the top, we've got Li and Gi. Looks like Gi's are opposites across the top there, so they will not be used in our solution, our resulting equation. So we will have to include not Li and X and Y. And remember, we multiply within implications and we add implications together. So this is the equation that we've found for GO. It's our simplified equation. I do like to keep similar results together, and so I put parentheses, keeping the parenthetical relationships together. We're going to be multiplying first within the parentheses, and then adding GI onto that as well. Okay, having finished that, we also need to K-map the LO column. This is a good time to stop the video, see if you can do it before I do. If you can, then you own this. Okay, here I go. So now I'm putting GIs across the top with double knot, left knot, no knot, right knot pattern, and XY down the side with the double knot, left knot, no knot, right knot pattern. And I am still going to be populating this K-map vertically because GI is on the top and GI is the first column. On the input column, it's the column on the left. That means we populate away from GI. And so I'm going to put 0, 1, 0, 0 in. 0, 1, skip, 0, go back, put the 0 in. The next column of 4, 1, 1, skip 1, go back. Skipping a whole column. We're going to the last column and putting in 0, 0, skip, go back. And then X's in the last column, X, X, skip, go back. Now we're looking for the biggest implications we can find. Of course, it's another group of 8 this time. There it is. Since we populated from top to bottom and implicated from top to bottom, all of the XY's cancel out. It looks like the GI will also cancel out, so we're going for this implication, all we've got is an LI. We'll put that in our equation now. We do have another 1 that is unimplicated, but we can group that in a group of 2 1s, making our simplification smaller. We're going to have to keep not X and Y. There's nothing to cancel those against, but up at the top we can cancel LI because one is knotted and the other is not. So the result here will be GI times X times not X, not GI times not X times Y. Okay, so what have we done? We have thought of an idea. We want to make a comparator. We've made a picture of a box with inputs and outputs. We have used that box to build our truth table. From our truth table, we populated a couple of K-maps for the outputs. We've implicated and simplified those variables GO and LO, and now we have these equations. So We could construct a 8-bit comparator, so the comparator could do a byte. That's a lot of redundancy, and I think my students can learn just as much by just doing a 3-bit comparator and saving time. We will be constructing this 3-bit comparator in Vivado, the application, using VHDL, Virtual Hardware Description Language. And we will only need to build the first comparator first, and then we'll be able to copy and paste that to make additional instantiations or instances of the original comparator. We could do 8 of them if we wanted to do a whole byte, but when we're done, we will have actually just made a comparator that can compare 3-digit numbers, and you just keep adding comparators if you need an 8-bit. So that's it. That's all there is for this video. And so join me for my next video, where we're going to actually start building this first comparator entity in Vivado. See you then. This is Aaron Jerome, Jerome Electronics. Bye-bye.